Okay, in this we're going to look at coral reefs and what controls their growth and all the different aspects of the reefs. Reefs are important from geology because many of the oil and gas and other deposits that are economically important are often found in reefs that are in older rocks and clearly buried below the surface. But in order to understand what's going on there, we have to try and understand how modern coral reefs grow. So, what are reefs? If you ask most people what a reef is, they simply say, well, it's where corals grow. But if you go back into the Oxford Dictionary, the original definition of a reef was it was a solid underwater structure capable of causing shipwrecks. Nothing to do with the animals or plants that live there, purely a shipwreck. This photograph on the from East Sound on Grand Cayman clearly illustrates the relevance of that. This ship ran aground on the reef there. There's also considerable debate onto what modern reefs are, because if you look at it from a biological or geological point of view, reefs are actually everything from multi-taxal constructions to piles of mud. And when we say multi-taxal constructions, we're saying these are features that are constructed by many different species and genera of animals. In most cases, the reefs are formed by various biological entities, such as corals, but not solely by corals. For example, if you go into Florida, there are reefs that are being constructed by worms. And if you go elsewhere in the world, there are reefs that are constructed by other organisms. That's important because the structure, these biological structures, which most reefs are, reflect the organisms that built them. They are extreme complex environments because there's loops between the organisms themselves, how the different animals and plants live with each other, environmental conditions, and evolution. Ancient reefs are not simply modern reefs with different organisms. A lot of the older organisms that grew and formed reefs had completely different ecological demands and attributes from the modern reefs. In many cases, those reefs, the animals that built them, have no modern counterparts. We also have to understand there are two types of coral in the broadest sense. There are the warm water corals. These are the ones that we're most familiar with. They're the ones that you see around Grand Cayman. And as that term implies, they require warm water to grow. What you may not be aware of, and very few people are the cold water corals. These cold water corals can grow in very deep water. The image shown there, for example, the corals near the Aleutian Islands in Alaska, growing at a depth of 2,800 meters. There is no light. It's pitch black. It's cold water. These corals, however, can grow for long periods despite those adverse conditions. So some of these corals in these cold waters can be up to 5,000 years old. Coral is obviously a living animal. The living animal itself only occupies the outer part of a coral head. So if you see a large coral head that's many meters in diameter, the living coral is only on the outer surface. The inner part is all its skeleton. These coral polyps are a very complex part of the coral. They're found in the outer surface. And if you look at the image on the right-hand side, the red areas that you see in the center of each of these corals, that's the mouth. These yellow tentacles that are sticking around it, those are tentacles. They waft around with water. And at the tips of each of those tentacles, there's a stinging cell. So the coral can, any prey or organism come around, corals can sting, kill it, and then drive that food towards the mouth of the coral. The fire coral, for example, it's found around the Cayman Islands and other islands. These are the ones that if you brush against it, you can get stung and react to it. That stinging is from those cells at the end of each tentacle. Modern corals, they do not feed during the daytime. So if you go down and look at the coral very closely, and it should be emphasized here, you never touch a coral. Corals are covered with a surface of mucus, sort of slimy material. That's its protective coating. That's what protects other animals from attacking it. If you touch the coral, you will wipe off that mucus, and then it becomes liable to attack by other animals and also various fungi and algae and everything. On the right-hand side shows a picture of a coral from Cayman Brac, and you see all the tentacles out, all those feeding in the mouths in the center. There are some corals around the Cayman Islands that get confused, and if you're really lucky, you can actually see them feeding during the daytime. But if you have to do it very carefully, because as soon as you make a slight movement, all these coral polyps will simply retract and you won't see them anymore. These warm water corals are very complex organisms. They have what's called a symbiotic relationship with another organism. In most cases shown here, these are dinoflagellates, and microscopic organisms. You wouldn't even really see them with the naked eye. In this photograph in the bottom here, it shows the coral polyp. You can see the sting cells at the top. And all these darker areas that are shown on the stems of the tentacles, those are these dinoflagellates. They're what we call symbiotic zooxanthellae. Very, very important. So the modern corals that we look at have these zooxanthellae. They have a symbiotic relationship, so both benefit from the other. And it appears that this is what allows the corals to grow very fast. The exact mechanism for that is not really known. It's also estimated that these zooxanthellae provide up to 90% of the coral's energy requirements. In return, the coral provides the zooxanthellae with protection, shelter, nutrients, and a constant supply of CO2. The growth of these corals, which are called hermatypic corals, are largely dependent on these zooxanthellae. The corals I showed previously that grow in the very deep water, they do not have the zooxanthellae. They lack. One of the things that is notable about modern corals are these periods of what's called bleaching. And if you look at the picture on the right-hand side, it shows you a coral from Grand Cayman. It's got that sort of greenish color of the living coral. But you look at it carefully, you can see little white dots on it. The photograph on the right side shows that coral after a period of what is known as bleaching. Same coral, living on the left, but it's lost its color on the right. The reason it loses its color is because, for various reasons which we don't fully understand, the corals eject the zooxanthellae, and hence you're left with the color of the skeleton. If that is a short temporary phase, that coral may allow the zooxanthellae to come back in and will live again and carry on growing. If the period of bleaching goes on for too long, the coral will probably die. So this is a very important process. With the warming of the oceans that seems to be occurring during recent years, This is a significant threat to these corals, and we may in fact lose a lot of the corals that we now see. Corals, modern reefs, and corals also require very well-defined environmental conditions. This is in addition to the fact that they require the zooxanthellae. Salinity must be what we would call normal salinity, so between 25 and 35 parts per thousand. If the salinity goes too low or too high, the coral will die. They just can't tolerate this really high salinities or fresh water. The water temperature must ideally be between 25 and 29 degrees Celsius. Again, if water temperature goes too low, below 18 degrees, or too high, above 36 degrees, corals are not happy, they will die. The corals need sunlight because they need to, for photosynthetic activity. And the depth of the photic limit is highly variable because it's largely controlled by the amount of sediment that's in the water column. So if you get a lot of suspended sediments in the water column, like mud, then that's not going to allow sunlight to penetrate, and therefore the photic limit is very shallow. On the other hand, if the mud is lost, the base of the photic limit is much lower. Corals do not like huge amounts of nutrients. It's almost counterintuitive. They're quite happy to grow and that, but they don't want a lot of suspended sediment. They don't eat a lot of nutrients. Put all these factors together, this is what we call the modern reef growth window. It's important to stress here that if we go back into the ancient succession of ancient reefs, these parameters may not apply to those because in the old rocks we have different types of corals, and it's not clear if they had the photosynthetic organisms associated with those corals. So this diagram here summarizes it, and what you have to understand is that if you take any particular parameter, such as temperature, too low a temperature is as bad as too high a temperature. It has to be right in that optimal range. And you can apply that general diagram there to any one of these criteria that are listed on the left. What it means is that corals grow in a very rigidly set environment. And if you affect any one of these criteria, you stand a chance of killing off the corals. Irrespective of what I've just said, reef construction, irrespective of age, is a function of various processes. It's a function of the in-place fixation of carbonate. By carbonate, we mean calcium carbonate, CaCO3, by organic assemblages of microbes, algae, and mesozoa. Again, we've focused so far on corals, but as you know from swimming around any of the corals and coral reefs around Grand Cayman, there are all sorts of organisms associated with it, the microbes, the algae, other plants, other animals. They all live together in a very complex ecosystem. Often as these corals grow and develop into reefs, you will get development of an internal cavity system. In some cases, you get caves formed, which you can actually go on scuba, you can actually swim into those caves. So a reef may give you the impression of being absolutely solid, but it can also have a lot of voids in there. We also get what we call synsedimentary lithification. This is where minerals are precipitated out from the ocean water, not by the corals or anything else, they just precipitate from seawater. Those minerals will be precipitated between the corals, the old skeletons, and in effect, they're a cement that help to hold everything together. On the negative side, you can also get what we call bioerosion. So if you look at this coral in this photograph, you'll see round holes in there. And if you look carefully, you'll see a round hole with what looks like a shell in it in the upper part of the photograph. These are actually bivalve shells. They're a bivalve that has the capability of boring into a coral skeleton. They do it because it offers them a safe place to live. But there's also many other organisms that do the same thing: algae, fungi, bacteria, worms. So it's a very complex ecosystem. We have to deal with what's called biological fixation of carbonate by calcareous metazoans. Carbonate, again, is calcium carbonate. Calcareous metazoa, these are the animals and plants that have got calcareous skeletons. So this aspect of building skeletons from calcium carbonate demonstrates so far in terms of corals. Some of the sponges will also do that, bryozoans and some of the bivalves. Most of the reef builders that we see in the tropical areas of the world, these are colonial corals. All the corals live together. They will call what we call obligate calcifiers. This means that in order for a coral to live and grow, it must produce a calcareous skeleton. It's the same way if you look at your own body, your body must produce bones to form your skeleton. You have no choice in it as part of the process. Many of these corals that live in the tropical areas are what we call hypercalcifiers. And that means that they're capable of producing vast amounts of calcium skeleton in very short times. But having said that, you also have to realize that because of the great diversity of corals, they're all different. Some corals like to form really large, complex skeletons. Other corals, they just form very delicate branching forms. And that's what gives you the vast variety that you see when you look at it. Next few photographs are going to show you some pictures of the corals. People living around Cayman Islands, you see these all the time. But just to have you look at these and think of these now in terms of the information that I've just provided. This is the Acropora palmata, very common in high energy environments in front of the reef. This particular coral grows very fast. It forms very hard, rigid skeletons. It has to, in order to survive the high energy conditions with breaking waves that exist in these environments. And these 4 photographs here, including the one I've just shown you, gives you a visual impression of the vast variation in the morphology of these different corals. Every particular genus of coral basically has a different growth form. What I've shown in the first part of this talk are aspects of the modern reefs. And what we need to look at now is how did these reefs form, how did they develop? To do that, we need to go back and look at some of the early work. And one of the people that was pioneered in some of this, although he's not particularly well known for it, was Charles Darwin. And he did publish a book, The Structure and Distribution of Coral Reefs. It was published in 1842. And he based out on work that he did when he was on the voyage of the HMS Beagle between 1832 and 1836. Remember that when he did this, no satellite maps and none of the information we have now. Scuba diving didn't exist. So this was done with very rudimentary tools or that. But what it reflects is a very keen sense of observation and interpretation. If you go into the Pacific Ocean, particularly into the Southern Pacific, you will see that you get atolls, quite different from what we see in the Caribbean, where you basically get islands with the corals growing around. And the atoll is characterized by deep water around its outside. It's got a central lagoon, which can commonly be very deep, extremely deep. And then land is simply that ring of land as shown here. Prior to the work by Darwin, Charles Lyell and Frederick Beechey are also well known for the early work. They suggested that coral would grow on the top of underwater mountains and volcanoes, that the atoll adopted the shape of a volcanic crater, and hence corals grew upwards from deep water. What is critical here is note that last statement: corals grew upwards from deep water. Darwin noticed, and based on his observation, that corals only live, or the modern corals only live, in clean, tropical seas, agitated water, in shallow water. And hence, it did not fit with the notion proposed by Lyell and Beechey that the corals grew up from deeper water. Remember, if it's in deep water, very little sunlight, modern corals need sunlight. So Darwin argued that the atoll evolved through a series of stages. Stage one was a volcanic island with an eruption. Volcanism stopped. When it stopped during stage two, that volcanic island started to sink. And as it sank, and shown in the white sort of grayish areas around the margin, a reef, a fringing reef, started to grow and develop. Stage three, the volcanic island is still sinking, but as it's sinking, the reef is also continues to grow upwards to the surface. You now see the start of the lagoon around the island. Stage four, volcanic peak is now below sea level. You're left with a ring around it where the coral has grown up, and we've got the central deep lagoon. James Dana in 1853 argued that Darwin was correct regarding his idea, supported Darwin's idea that substance was the key behind this. In 1916, Reginald Daly argued that Darwin was wrong. The reefs are just thin veneers that rest on submarine banks. He argued that those banks form when periods of glaciation. What you have to remember here is if you increase the size of the ice caps in the North and South Pole and you produce ice caps elsewhere in the world, the water to form that ice comes from the ocean, and as a result, sea level will drop, and that allows exposures of banks once underwater. And then as the seawater rose again, then reefs started to grow back and continue to grow. So he disagreed with Darwin's idea. You have to remember when those geologists I've just mentioned were doing their work, there was no scuba diving, there was no underwater submarines to do it, there was no knowledge, real knowledge of the rocks at depth. Later on, and I'm sorry to back up, Darwin estimated that the succession of reef material on these islands might be up to 5,000 thick, 1,500 meters. Eniwetok Atoll was in the Pacific Ocean, and Eniwetok was an island that was affected when the USA did their first experimental explosion of nuclear bomb. They blew up in the Pacific. And prior to doing that, they drilled a deep well on Eniwetok because they wanted to find out what rocks looked like before and after the explosion. And they found the core, and some of the core is shown here. They found that the reef rock, as they called it, i.e. the rock formed the corals, and that actually went down to a depth of 4,610 feet before they hit any volcanic material. Rather remarkable, because you look back at Darwin, he estimated that reef material might be up to 5,000 feet thick. It was an estimate. He had no way of knowing that. But look how close he came when they actually drilled the well and found that difference. And the key here is that even when you went to the depths and deep parts of this core, all of the corals that they found in that deep part of the core were indicative of growth in shallow water. The corals simply couldn't grow at the depths which are now found, and hence that supported Darwin's original idea. There are various ways that we can date the old corals. We can use carbon-14, and if we use carbon-14, it showed that some of these corals at the bottom of these cores were up to 50,000 years old. And we can then look at the ages of these to get estimates of water depths throughout the coral that we find. This is illustrated here by a coral that was dredged from near Bermuda. Coral weighed 1,000 pounds, just to give you an idea of the size of it. And by dating this, they showed that that coral took 200 years to grow. And just to put in context, they've put various historical timelines on there just to give you an idea. So here, corals born in 1600, bacteria discovered in 1676, first steam engine in 1710, American Revolution in 1776, just to put it in context. Again, it supports the idea that was proposed by Darwin. So Darwin is a very astute and kind of proved his point. As a geologist, or as geologists, we are interested in reefs through time. On the right-hand side, it shows what's called a geological column, going back to the Archean of 3,000 million years plus, very, very old rocks. And even if you go into these older rocks, there are still evidence of reefs. They're not reefs in the sense we know now. They're reefs in the sense that they're structures that were built above the seafloor, built by different organisms. In the case of these old ones, they're built by fungi, algae, bacteria. And it's not until we get here into the Silurian, Devonian, that we see evidence of coral reefs. But what you have to understand here is the corals that form those reefs are different from the corals in which we find the modern reefs. They're a different branch of the coral family. And then we get periods of time where there's very little evidence of coral reefs. And then, for example, during Triassic, Jurassic, abundant coral reefs. And again, now in the Cenozoic, abundant coral reefs. So they come and go. It's a reflection of the state of the oceans, the animals. And it's important to note that these reefs, through time, have been formed by many different types of animals and plants. Why reefs are important in the past, for example, if you look at the Devonian reefs, about 350 to 400 million years old, in Western Canada, close to where the University of Alberta, where I live. If we go and drill wells, we can penetrate these older reefs, and that is commonly where there are significant amounts of oil and gas reservoirs. So these reefs are ideal for that purpose. On Grand Cayman, you can go see examples of some of the older corals and reefs. This is on the northeast coast of Grand Cayman, where you see the Iron Shore Formation. When you look at it like this, it just looks like a scene of gray weathered rocks. However, if we go closer in, these are actually formed of beautifully preserved corals. These corals have still got their original skeleton. They've not been changed. But here, for example, you see a coral head that's been broken open. You can see its internal structure. On the right-hand side are pictures of different corals. These corals, the species most of the species you find in here are exactly the same species that you find in the modern waters around Cape.